I'll welcome everyone to the final, last but far from least, plenary session of the conference. It's good that so many people have stayed around, and it's been a wonderful conference, by the way. I know John said great things yesterday evening to thank program committee, local organisers and everything, but just to say it's a fantastic event, so thank you very much for that. Before the Sargan lecture, we traditionally give the Sargan Prize, award the Dennis Sargan Prize. If you look in your booklet, you'll see a whole page on the Dennis Sargan Prize. And this prize is awarded for the best unsolicited article published in the Econometrics journal by anyone who is within 5 years of being awarded their doctorate, at least when it's published. There's an honorarium, £1,000, that's rather nice. I've got a certificate, but I don't have the cheque. But I presume that it's still healthy. The winners decided by the Econometrics Journal's editorial board, managing editor and co-editors, and just to, I don't know whether any of them are here, but just to point out, the journal's doing very well and very exciting papers. And it's particularly nice, this particular choice of paper couldn't be more appropriate. The winner is Hei-Ching Xu of University of Texas at Austin for his paper, Estimation of Discrete Games with Correlated Types. So, Hei-Ching, why don't you come up here? While you're coming up here to get the up. I can stay up here a second, because I'm going to tell you a little bit about, the paper. Why did I say it was a good paper? It's not just a very good paper, it's also a paper that combines econometrics, some theory and some application in a rather fantastic way, actually. It's a two-player binary game in which the players' payoffs vary with observed covariates, but also privately observed types. And the key idea is to allow these types to be correlated, which he shows, by the way, empirically important. But just allowing them to be correlated causes some difficulties. And in particular, in the standard estimation methods, you get multiple equilibrium, of course, and standard estimation methods become inapplicable. And what he does is propose a very nice two-stage method that first identifies and estimates a subset of the covariates for which the equilibrium is unique, and then estimates the model that you just use in standard models. So it's a wonderful paper, and congratulations to Hei-Ching for this Sargan Prize. Thank you. I'm going to move on. Well, I'll get while we're doing that. So now on to the Sargan lecture. It's a wonderful pleasure to introduce Susanne Schennach from Brown University, professor at Brown University, to give this Sargan lecture, 2016 Sargan lecture. And Susanne is fellow of the Econometric Society and international fellow of Cemmap. She's especially well known for her research on measurement error and has a really wonderful review just been published actually in the annual review of economics. But if you look at her vita or followed her work, she started in a way, at least from econometrics perspective, with remarkable papers, a sequence of papers really, in econometric theory, econometrica and biometrica, which certainly changed mine and changed many of our view of how identification and estimation of nonlinear models with measurement error, how to think about them, and how to go about identification estimation. As far as I can see, it's kind of revolutionized the way we do nonlinear models. I'll give you one example. She published an Econometrica paper with Jim Heckman and Flavio Cunha I know the other two authors quite well, and they'd been floundering around for quite a while, I think, on how to deal with measurement errors and unobserved individual effects, in fact, in nonlinear production functions. And along comes Susanne. And together they produce a remarkable paper in Econometrica. And as I talk to many applied workers, certainly among my colleagues, they use that paper and that idea regularly. And of course, she's gone on to produce many other beautiful papers in this field. So that's enough, and I'll hand over to Susanne to give the Sargan lecture for this year. Thank you.
All right, this seems to work. Perfect. Okay, thank you very much, Richard, for this wonderful introduction. It's an honor to be here and give the Sargan lecture today. And thank you very much for staying around. I know it's almost the end of the conference, so this is much appreciated. All right, today I'm going to talk about learning from errors. And as we go along, what I mean by errors will become clearer. To start, I'm going to give two random examples, one drawn from the physical sciences and one drawn from economics, to illustrate why errors are particularly important in economics. To be inspired, for an example, in the physical sciences, I looked at something that's of particular importance to people living along the coasts, like myself in Rhode Island or people here in Brighton. And that is the well-understood problem of predicting tides. Now, this is a situation where the basic mechanisms and variables are well understood, so it's not surprising that the quality of the prediction is very good. In many social sciences and economics in particular, we're not as lucky. Let's say that you're interested in the relationship between adult income and cognitive skills at an earlier stage. There is a clear relationship between the two, and if you were to test it statistically, you would find that that relationship is statistically significant. But there's a huge amount of scatter, and cognitive skills explains a fairly small fraction of adult outcomes like income. Now, the reason between the difference in the two is because in the one case, in the physical science, in that example, the underlying variables are well observed and understood, while on the other hand, in the economic example, cognitive skills are certainly measured with error, and there are many other factors that show up that we don't observe, and that basically that is shows up as noise to the modeler. Of course, these are two examples drawn from the extreme. Most prediction problems, both in the physical sciences and in economics, fall somewhere in between, but situations in economics often look more like this problem than this problem. So we need noise in economics because humans are hard to predict and not all alike. So even if human beings are put into the exact same situation, they won't all behave the same. So we really need noise to, in our models, to account for a number of not mutually exclusive and overlapping regions. Our models are imperfect, and that imperfection shows up as noise. Then we have heterogeneity, and that heterogeneity can be modeled as noise. And of course, then there are just data limitations. Some variables may be unobserved or latent. Other variables that we do observe are measured with error. So it's not surprising that the analysis of errors has been receiving increasing attention. To fix the ideas, let's say that we have an observed a true variable of interest, x star, that's unobserved. Instead, what we observe is a variable x, that's basically a mismeasured version of x star, so it's x star plus a measurement error delta x. Now, since there are two unobservables and just one observable, we won't be able to recover the truth at the level of the individual observation, but thankfully that's often not needed. Okay? Often what is sufficient is to recover the truth in some average sense. So let's say that you're interested in the effect of an intervention on the economic well-being of individuals, and you're interested in the average effect on some subpopulation. And that average point is key here because, again, you may be able to correct for the measurement error in an average sense. Okay? And to see roughly how, let's say that you have a sample of size n, and then you average your observable over that sample, and that amounts to averaging the truth, x star, and averaging the measurement error. And then if your sample is large enough, we know that we can invoke the well-known law of large number asymptotically so that the averages go to the expectations, the corresponding expectations. And if the measurement error is classical, so has zero expectation, then the measurement error is essentially averaged out asymptotically. So that is a kind of idea that underlies many measurement error models, but in more sophisticated ways. And that is because most useful models and estimators in economics are actually nonlinear in the mismeasured variables. Even a basic OLS is nonlinear in the regressors. And as soon as you have nonlinearity, this additive separability into signal and noise no longer works. Situation is, of course, even worse if you have non-classical measurement error, so if the measurement error does not have zero expectation. There are many different ways to deal with measurement error. A surprisingly large literature assumes knowledge of the distribution of the measurement error, especially in statistics, and then it's fairly easy to correct for measurement error using the deconvolution theorem, and we'll see that shortly. Of course, many economists are unwilling to make such a strong assumption. And one way around assuming the distribution of the measurement error is if you have so-called validation data. And validation data is a setting where, in addition to your main data set, where the main data set contains the variables measured with error, you have an auxiliary data set that contains observations on the perfectly measured variables. Unfortunately, validation data is typically very expensive to collect or often impossible to collect. So there are relatively few cases of validation data available. So people have tried to devise approaches that are less demanding in terms of data and developed approaches, for instance, based on so-called repeated measurements. And a repeated measurement is basically a situation where we have more than one measurement of the underlying unobserved true variable. And that could come from measuring the same variable repeatedly over time, or interviewing two different people about the same quantity, like interviewing a husband and wife about household income, or simply measuring the same quantity in different ways. People have also tried to develop approaches based on instrumental variables, which in some sense are more general than repeated measurements, in the sense that they could be measured in different units or be non-linearly related to the truth. And then if you don't have such additional information, like repeated measurements or instruments in your data, then sometimes people have proceeded to make strong assumptions and use higher order information from the existing data set. So higher order moments beyond means and covariances. That is typically done under stronger assumptions. If one is unwilling to do that, sometimes the best one can do is bound the parameters of interest. So here, just before we proceed, just an illustration of something that you don't want to do. If you've never worked on this, you might think that minimizing the sum of the orthogonal distances squares seems like a good idea. But that is not the case. One reason is that orthogonality has no meaning if x and y here are in different units. And even if they were in the same units, then picking the orthogonal distance would assume that the ratio of the error variances along x and y are magically related to the slope of the regression function. Why is that? Well, let's say that you have errors only along y, then you want to minimize the, sum of the vertical distances squared. If you had errors only along x, you would want to minimize the sum of the horizontal distances squared. And then picking some diagonal distance would assume that you know the ratio of the variances of the errors. Okay? And picking the orthogonal distance in particular would assume that that ratio is determined by the slope of the regression line, which makes no sense because the slope of the regression line is related to the truth, the signal, while the error variances are by definition about the noise. Okay, so this is something that you don't want to do. First, assuming that the distribution of the measurement error is known, then we can use kernel deconvolution. And a lot of problems in the measurement error literature, at least in the classical measurement error literature, rely on Fourier transforms. And this slide summarizes the main reason for the use of Fourier transforms in this literature. So again, let's say that you have an observable x that is equal to the truth x star plus a measurement error. The measurement error is independent from the truth. Then we know that the distribution of x, the observable x, is just a convolution of the distribution of the truth with the distribution of the measurement error. Now, a Fourier transform just writes a distribution as a linear combination of complex exponentials. And here I'm writing down the Fourier transform of f of x. And that is sometimes called the characteristic function. Characteristic function here, the characteristic function of x. And if you Fourier transform the convolution between x star and the measurement error, go through a few steps, you get the product of the characteristic function of x star times the characteristic function of the measurement error. So you've changed a convolution into a product, and products are much easier to deal with than convolutions, and that's really the main reason for the use of Fourier transforms. There are other nice properties, but... all right, so having said that, kernel deconvolution is really fairly simple. Again, you have x equal to the truth plus a measurement error. The measurement error is independent from the x star. And then we have our convolution that becomes a product. So the characteristic function of x is equal to the product of the characteristic function of x star times the characteristic function of the measurement error. The characteristic function of the measurement error, so the distribution of the measurement error in this case is assumed known. We can observe the characteristic function of x, so the mismeasured variable, and we're interested in the characteristic function of x star. So here we can just take a ratio. This assumption here is that the characteristic function is non-vanishing. It's a very weak assumption. In many cases, this can actually be relaxed. So here, now we have to estimate, of course, the density of x, or the characteristic function of x. Estimating the density of x is in real space just a convolution of the empirical density and the kernel smoothing, and that convolution in Fourier space again shows up as a product after Fourier transforming it. So, and here we have the empirical characteristic function, so the Fourier transform of the observable distribution times the Fourier transform of the kernel, and that is our estimate of the characteristic function of x star. And you can plug that into this ratio here, and then take an inverse Fourier transform to get from estimate of the characteristic function of x star to the an estimate of the density of x star. Okay, simple enough once you've assumed that you know the distribution of the measurement error. Many economists are unwilling to do that, so let's see what can be done in that case. Unfortunately, standard instruments that are instrumental variable techniques that are used to deal with other types of endogeneity in economics don't work for measurement error, nonlinear measurement error models. So here we have an example of a regression, a nonlinear regression, where y is nonlinear related to the truth x star plus a model error. X star here, again our measurement equation, is just x minus the measurement error. You can add and subtract g of x, and then you have a regression relationship between y and x, and an effective error term epsilon that in general depends on x. If the specification is actually linear, then the dependence on x in the error term cancels out exactly, and you can't think of finding a standard instrument that's correlated with g of x but uncorrelated with the error. But if the specification is nonlinear, then this dependence on x in the error term does not cancel out, and you can imagine that it's difficult or impossible to find an instrument that's correlated with one function of x, but correlated with one function of x, but uncorrelated with another function of x. So we need approaches that are specifically designed to deal with measurement error in nonlinear models. For polynomial specifications, Hausman, Ichimura, Noe, Powell derived a very nice closed-form solution that expressed basically polynomial coefficients as a recursive function of observable moments of the data. And that worked for both instruments and repeated measurements. For more general specifications, at least with instruments, with repeated measurements, not for instruments, Hausman, Noe, Powell used the fact that an arbitrary function on an interval can be approximated via a sequence of polynomials. And also for repeated measurements, Lee used a solution based on Kotlarski's identity, which we'll see next. So Kotlarski's identity is a very old but very useful result. We basically have two measurements, x and z, that are observable, two measurements of the underlying true x star. Here, the measurement errors and x star are mutually independent. At least one of the measurement errors has zero expectation. And then it turns out that you can get an expression for the density of x star just in terms of moments involving the observable. That is much more sophisticated than standard kernel deconvolution, because you don't assume that you know the distribution of the measurement error. Instead, essentially, you're estimating the characteristic function or distribution of x star using the two error-contaminated measurements. It's also more sophisticated than assuming that you have a lot of different measurements at each value of x star and then averaging over them to average out the measurement errors at each value of x star. Because here you need only two measurements, because averaging implicitly also occurs over different values of x star. So you need only two measurements. This setting has been extended to multivariate setting by Li and Luong, and to a regression setting by Lee. And then you can actually relax several of the assumptions, the independence assumptions from Kotlarski in various ways. Here is an early way of doing that. Okay. Basically now you have, among other things, the measurement errors on the two measurements no longer need to be independent. And also the variance of one of the measurement errors can actually vary with values of x star. Another refinement here is that we're expressing things directly, we write things directly as an expectation of a known nonlinear function of x star, which turns out to simplify the derivation of the asymptotic results. And again, you have that just in terms of observables. Of course, phrasing things in terms of moments, it becomes clear that we can now deal with most estimators in the presence of classical measurement error. So for instance, nonlinear regressions impose moment conditions that comes from the first order conditions of squared residual minimization. GMM is directly written in terms of moments. Maximum likelihood can be written in terms of moments via their first order conditions. And you can even allow this function of x star to depend on sample size via bandwidth or smoothing parameter, and then you can do non-parametrics. These results were using repeated measurements. Once you have instruments, the situation is actually a bit more complicated. This slide builds upon the early work from Hausman, Ishii, Powell for polynomials that was then reconsidered by Nui and Wang and Shao, although without general identification results. And here we have a nonlinear or non-parametric regression setting. Only one observable measurement of the truth x star, but we have an access to instruments that are nonlinear related to the truth, but not related to the errors. Still one independence assumption here. In that case, you can again express in here the regression function of interest in terms of just observables. This expression is a bit reminiscent of the Kotlarski type results, but it actually involves more complicated quantities like Fourier transforms of conditional expectations and the various divergences that have to be taken care of. And then when the regression function is parametrically specified, turns out that you can just derive equivalent moment conditions and then use standard techniques to derive the asymptotics. This treatment has been extended to quanta regressions, which in turn allows you to identify the joint distribution of a dependent variable and x star, which means that you can then go to more general models beyond regressions. Everything that we've talked about so far assumed classical measurement errors, so measurement errors that have zero expectation. And really the vast majority of the literature does exactly that. One way to relax this classical measurement error assumption of zero mean is to assume that the distribution of the observable is in some sense centered at the truth. Now that censoring can be almost anything, but it has to be specified by the researcher. And so, for instance, you could replace the zero mean assumption by a measurement error that has zero mode, zero median, some other zero quantile. This alternative measurement error assumption has received support from some of the existing validation data evidence. So here I'm reproducing results from Bollinger, who had validation data for self-reported income. And the validation data was from Social Security income in the US, so basically government data that was assumed to be the true income. And what he found is that the mean of self-reported income, conditional on true income, did not fall along the diagonal x equal to x star. In particular, the poor tended to over-report income. On the other hand, he found that the median of self-reported income, conditional on true income, did lie along the diagonal, which would suggest that a zero median assumption on the measurement error would be valid, while the classical measurement error assumption would be invalid. And then for the same data, it was found that at each quartile of true income, the self-reported income was at the truth, which would suggest the mode of self-reported income was at the truth, and that would suggest that a zero mode assumption would also be valid in the setting of self-reported income. This kind of alternative centering restriction is also useful when you have measurement error with other data problems. Okay, and here I'm graphing density of x conditional on x star without worrying about normalizations. But if you have truncation, for instance, truncation affects the mean, but it preserves the mode, at least as long as the truncation isn't too severe. And if you have censoring, well, censoring affects the mean, but it preserves the median as long as the censoring isn't too severe. And finally, you could have some very extreme measurement error problems. For instance, always over-reporting or under-reporting. And for instance, if you have systematic under-reporting, then you, which might be the case with self-reported alcohol or drug consumption, then you might be willing to assume that the truth is at the 100th percentile. Yeah? And that would also be covered. So now to be more precise, let's say that we have at least access to at least 3 error-contaminated measurements of the truth, x star. Okay. Some of these measurements could be distorted measurements of the truth. Okay, so they beyond repeated measurements. Some of them could be instruments, or even the dependent variable of a regression might be taken as a measurement. Yeah. And then the goal would be to use the observable density of the 3 measurements, and I'd call the 3 measurements x, y, and z, in order to identify the unobservable distributions that involve x star. If the observables x, y, and z are mutually independent conditional on the truth, then you can write this integral relationship between the observable distribution and the unobservable distributions involving x star. And the question of identification then amounts to asking if there's a unique solution to this integral equation. If one of the measurements is centered at the truth and some other technical conditions, the answer to that question is yes. And the proof proceeds by writing this integral relationship here as a composition of 3 linear operators that can then be shown to be the spectral decomposition of some operator, and that spectral decomposition can be shown to be unique. This result can be seen as generalizing the well-known and widely used linear factor models to nonlinear and non-classical settings. And it can also be seen as one generalization of the discrete factor models along the lines of Kruskal's work to continuous distributions. So far, validation data, repeated instruments, repeated measurements or instruments. What if you don't have access to such auxiliary information? Okay. Well, then let's go to a very simple setting, linear regression model with one regressor. X star and the measurement errors are mutually independent and have zero mean. So a fully classical setting, very classical setting, we have just this one measurement of the truth, so no other outside information. Yeah. And now, in terms of identification, what some people would consider the baseline case, where everything is normally distributed, is actually not identified. Yeah. And the normal here plays a special role because linear combinations of normals is still normal, and normals are entirely determined by the means and covariances. So you can't hope to make use of higher order moments for identification purposes. As soon as some things are not normal, then there is hope of identification. And people have used higher order moments or cumulants for identification in these non-normal settings. And there is a fairly large literature on that, even quite recently. Yeah. But what if you go beyond this linear regression setting to a nonlinear regression or non-parametric regression, still fully classical setting? Okay. Do things become better or worse? Okay. Now, in some sense, things actually become better because the pathological normal case from the linear setting is no longer an issue once you have nonlinearity. And that may not be too surprising because the nonlinearity in the regression, G, actually destroys the normality of some of the variables. What is perhaps more surprising is that in this fully non-parametric setting, the only functional form that may not be identified is this 4-parameter family. And even in that case, you're not identified only for specific distributions of the measurement errors and the truth. Okay, so identification really is the rule rather than the exception. Of course, if you have a linear regression, then the case it falls back to Weiersol's case, not surprisingly. All right, but still, keep in mind, still fully classical setting. Many applied researchers are not willing to make such strong assumptions, and rightly so. So what can you do if you're not willing to make these strong assumptions? Sometimes the best you could do is think of deriving bounds and inequalities on the parameters of interest under minimal assumptions. And to just motivate set identification here, in measurement error models and more general latent variable models, proving point identification is often quite difficult and usually requires some strong assumptions like independence assumptions. At the same time, if you focus on an identified set instead, that set may still be sufficiently small to show that a hypothesis is unlikely to be true. So ideally, you want researchers to be able to impose only the assumptions that they're willing to make, and then the method would indicate what inference can be made from the data. Before we proceed, I should mention that analytic derivation of the identified set is often exceedingly difficult or even impossible. One of the simplest and earliest examples of an identified set actually comes from the measurement error literature. Here we have again a linear regression setting, fully classical, and in that case, if you regress the observable y on the observable x, it turns out that you get a lower bound on the slope coefficient beta of interest. Now, the situation here is entirely symmetrical between y and x. So you can think of regressing the observable x on the observable y. Then take the inverse of that slope coefficient, and then you get an upper bound on the slope coefficient beta of interest. So you now have a lower bound and an upper bound on beta. In the pathological normal case, these bounds are tight, so without further assumptions, you can't really do better than this. This has been generalized to multiple regressors by Klepper and Lemur, but still very simple setting. And how can you think of generalizing bounds to much more general models with unobservables? Well, let's think about the generalized method of moments, where you impose an expectation of a nonlinear function g of the data x and a parameter, a vector theta. Okay? And that expectation is equal to 0. This setting is simple enough so you can give very general results, but yet general enough that you can deal with most estimators in economics. So now let's think of generalizing that to unobservables. Okay? So way of doing that would be to include the unobservable variables as arguments in the function g that defines the moment conditions. So in principle, easy, but effective. So here this u, these unobservables, could cover measurement error models where u could be the true value and the true unobserved value of the regressor, say. If you have interval value data, u could be the true position within the interval. If you have factor models, u could be the unobservable factors. If you have state space models, u could be the hidden state. If you have unobserved heterogeneity, u could be the individual type. Now, even though conceptually it might be difficult, of course, effectively it's a very difficult problem because you have to consider every possible distribution of the unobservables that could make the moment condition satisfied for a particular value of theta. Okay, so very high-dimensional question. Fortunately, you can focus on a much smaller class of distributions. You can just think of all entropy-maximizing distributions of the unobservables that makes the moment condition satisfied. Entropy maximization has a long history as a device to model lack of information, and it spreads the uncertainty as much as possible. And so here, what is interesting is that you have this exact equivalence, and you can say even more. It turns out that here, the entropy maximizing distributions have an explicit expression as an exponential family of distributions indexed by a small dimensional parameter vector gamma. So gamma has a dimension of g. And gamma summarizes everything you need to know about the distribution of the unobservables. And then, amazingly enough, you end up back to a GMM problem involving only observables and a slightly augmented parameter vector theta tilde, where theta tilde now contains the original parameter vector of interest, theta, and this nuisance parameter vector gamma that has the same dimension as g. And so let's see what this gamma does in a simple example with just two moment conditions that are supported from -1 to 1. In this case, this entropy maximizing distribution is an exponentially tilted version of the uniform. And here I'm graphing that for these two moment conditions, u and u squared minus 1. And then as you tilt gamma along one direction, that distribution concentrates along that direction until you reach a point mass. And then you can tilt it along different directions. And by doing that, you can reach distributions that have a mean anywhere within the convex hull of values of G, which is the same range of means that you could reach by considering all possible distributions of the unobservables. And then you can use simulation techniques to get back to moment conditions involving only the observable x. So the way I like to look at this method is really that you replace the non-parametric distribution of the unobservables by a least favorable entry maximizing parametric exponential family of distributions, indexed by this parameter vector gamma that has the dimension of G. Least favorable in the sense of that it doesn't make the problem any simpler than the original non-parametric problem. And then you can use the parametric method of simulated moments, but avoiding distributional assumptions. Okay, so basically you replace your distributional assumptions by this entry maximizing exponential distribution. Okay? And then that's why I called this approach entropic latent variable integration via simulations, or simply Elvis for short. So what Elvis does, it replaces this infinite dimensional distribution of the unobservables by a low-dimensional parameter vector gamma. There's no need to try to solve for the possible distributions of the unobservables. Instead, you have a computer-intensive but automatic simulation-based approach. The nicest thing here is there's no point of proving point or set identification analytically. This approach covers both, regardless of the situation, without analytic work. And the equivalent moment conditions involve only observables and are actually computationally well behaved with respect to gamma. And so just a couple of examples. The examples here, even though this is for general latent variables, I'm taking them from the measurement error literature because that's what I focused on in most of the talk. Here we have this simple linear errors and variables model that we've seen a couple of times. And we know that in the classical setting, if everything is normally distributed, you're set identified. And here are these little diamonds are the upper and lower bound from the forward and reverse regression, which you could do in this example analytically. And now what is nice to see is that Elvis can nicely distinguish whether you're point or set identified. Okay, so here you impose a large number of moment conditions to make use of higher order moments. And in the normal case, can you actually see the objective function here? I can barely see it. So here in green, you have an objective function, the objective function from Elvis. And that is pretty much flat between the upper and lower bound that we can derive analytically in this case. While in the non-normal case, the objective function has a much clearer maximum. Okay, so Elvis nicely picks up the different situations in this setting where one model is point identified, the other one is set identified. Of course, this is a case where you wouldn't really need Elvis because you could do everything analytically. But what about more complicated models? Well, in terms of errors and variables models, think of what is or should be a simple errors and variables model, a polynomial, where here we know from Schennach and Hu that under full independence, everything is point identified. But nothing is really known about what happens if you just impose a few moment conditions and imposing zero mean and uncoordinated assumptions. Elvis doesn't care. Here's the objective function, which I hope you can see, for the parameters from Elvis. And then here are the level curves for 2 different levels of significance, and the trues in blue. Again, this is, situations like this would be much more difficult to do for general moment conditions analytically, if they could even be done. And that's where Elvis is really particularly useful. All right, so one thing that excites me about having worked in this measurement error or latent variable literature is that the techniques that have been developed go in importance well beyond just pure measurement error. So, for instance, in auction theory, people have used bits as repeated measurements of an underlying common value. In panel data, people have used measurement error techniques to identify panel data models, for instance, using outcomes over time as repeated measurements of an average outcome. So there are techniques that use Kotarski type results and Schennach type techniques. Factor and state space models, where you can have generalized repeated measurements, where each observable indicator measures more than one unobserved factor. And then there are recent working papers on demand systems that use Elvis to deal with unobserved heterogeneity. Okay, particular job market candidate this year, one of the students at Brown is working on that. Okay? So I find that very exciting, and I'm going to talk the last few minutes that I have about these dynamic factor models a bit more, because as Richard was nice enough to mention, I've worked on that with Kunal and Heckman. Yeah? So I'm not going to do the paper full justice here, but just to summarize, we had a nonlinear dynamic model of skill formation with interactive cognitive skills, non-cognitive skills, and investments into skill. And then the focus was on adult outcome measures, such as schooling, attainment, or crime. And the model was basically a dynamic factor model where we had a lot of noisy measures of the unobservable skills and investments into skills. Okay? And so in principle, the techniques developed could allow for a non-separable and potentially non-classical error structure. So here, the basic setup, cognitive skill in the future period was nonlinearly related to cognitive and non-cognitive skill at time t, investment into skill, parental skills, and some potentially non-separable error term, shock. Then here, this similar equation for non-cognitive skill development. And then human capital and adulthood was related to cognitive and non-cognitive skills at the last stage. And you can also, again, this doesn't do it justice, you can also model investments. But the basic idea here is that, of course, skills and investments are inherently unobserved, while we do have many observable measurements. So we had multiple measurements for cognitive and non-cognitive skills for both the children and their parents. For cognitive skill, it has long been recognized that there is measurement error and it's not negligible, but you can imagine that if you were thinking of something like non-cognitive skills, there would be, the measurement error situation would be even worse, and that does turn out to be the case. And parental investments into skills, so these are just examples that we had: number of books in the household, time that the mother reads to a child, availability of musical instruments, amount of time spent with different people, frequency of trips to museum, and so on. And so clearly you can fathom that these would be very noisy measurements, and so it's crucial to allow for measurement error techniques. Now the model estimates then ended up suggesting that cognitive skills were most changeable early in life, while non-cognitive skills were changeable or malleable not only early in life, but also later on into adolescence. And that would then suggest that remediation strategies for disadvantaged children later in youth should really focus on fostering non-cognitive skills, because you couldn't really affect cognitive skills at that stage very much. And it was also suggested that investments in the early years were particularly important for the adult cognitive skills. Now, one concern to policymakers, the simulations from the model suggested that there was no trade-off between equity and efficiency in this case. Okay, so if you wanted to maximize aggregate schooling or minimize aggregate crime, okay, the optimal investment strategy was really to target the most disadvantaged at younger ages. We're not claiming that this is the last word in the study of interventions on skills, but it does illustrate, and this is again something that Richard hinted at, that it really is important to account for measurement error, in this case to uncover important features of the learning process, and doing so in these nonlinear settings is now feasible thanks to newly developed techniques. So as a conclusion, we've seen that the measurement error history goes back to a long way, with a lot of results for linear models, and then in the last quarter century or so, the focus has been on nonlinear models, which are the most widely used models and are widely used nowadays, okay, in economics. And recent results really try to cover nonlinear models from all angles under weaker assumptions, more readily available types of information. Okay? And in terms of future directions, our brains, we don't really tend to become all that much smarter, but computing power does tend to improve. So, so methods like Elvis or other numerical-based methods may help us take advantage of increasing computer power and large data sets. And then measurement error or latent variables don't show up in isolation in economic work, and combining these techniques with other problems, I think, is also important, and especially in applied work. And finally, while I didn't talk about that, it has been recognized that what we now know in terms of what kind of information can provide us identification and be used for estimation purposes can really guide the surveys, economic surveys. So for instance, it might be more useful in an economic survey to try to get multiple error-contaminated measurements of the truth than one fairly precise measured variable that is still contaminated with some error. So I'm going to conclude with that, and thank you very much again for staying around, and hope you have a good trip back.
Thanks very much. That was terrific, of course. Are there any... We have a few minutes for questions, not the best organisation for questions, but has anybody got anything they would like to ask? Andrew. Oh, is the one at the back? Andrew Cheshire.
Thanks for this nice talk, and it's not the moment to ask deeply technical questions. But
I can hear that.
thank you. I think an important message here is that measurement error really messes you up. It's interesting, actually, at the start of econometrics, Leo Hurwicz's first paper, where the econometricians of the 40s struggled with the idea of should we have many errors in each equation or just one error in each each equation, and they realized very early on that life was much, much, much simpler if they had one unobservable at the end of the equation and everything else was measured without error. But it's people who design surveys and gather data don't fully understand, I think, because of the original average. You can average out measurement error if you're just interested in means, but you can't do it once you have nonlinearities. There's tremendous value in measuring things accurately, and indeed, as Mansky started doing many years ago, starting to try to measure those apparently unobservable concepts that economists struggle with, rather than leaving them as unobservables in the data, measures of risk aversion, measures of people's expectations, and so forth. I think that's a very important message here. The other thing I think is that tricks and particular assumptions that deliver point identification are it's not perhaps the way to proceed, because we can't believe in these particular restrictions that happen to deliver point identification. I think your work on Elvis is very important there and needs to be taken further. But policymakers have to understand they'll never know with any precision, even with enormous amounts of data, the parameters in realistic economic processes. But thanks very much.
Thank you very much. Yes, and I completely agree. And of course, with the last point, I mean, ideally, you'd just be able to make some assumptions that you feel comfortable with, see what happens. Make other assumptions, what happens in that case. And then people can, so, and then that, with techniques like Elvis, that is now within the realm of possibilities.
No, I think that, I was very pleased to hear that Elvis is still alive. But also, as you were so the way Elvis works, you put no real constraints on you, as far as I can see. So maybe it's obvious, but I suppose one question: if you have some prior ideas about what you looks like, is that so?
So in general, you would want to know what is the possible support of you. If you don't, so if in truth you is compactly supported, but you don't, as a researcher, you don't know that, and you just obtain, assume infinite support, then this Elvis method is going to give you valid but conservative intervals. Of course, ideally, you'd be able to incorporate the distribution. If you have extra information, that can also be modeled in terms of the moment conditions. If you have distributional assumptions on you, then Elvis is not the way to go, and then you push back to more parametric setting. But there are certainly ways in which you could be analytic in some ways and numerical in other ways. So this is again something that I think is really opening up that kind of possibility, where you ideally, if things are easy analytically, you deal with those things analytically. If things are not easy, then you deal with things numerically. And a lot of different things you can impose via moment conditions.
Thank you very much. That's great. So let's thank Susanne again for tea is served.
And I'm going to head straight out.
Yeah, I knew you were. It was brilliant as ever, very clear. And great, that's fantastic. So thank you.
Thank you so much.